Okay, welcome to another tutorial where we're going to use the TinkerCad Arduino simulator and a few other tools to take a look at how we can make our Arduinos do amazing and interesting things. And today we're going to take a look at motor control using our Arduino and how we can model that in TinkerCAD simulation tools. So the first thing we want to talk about is the fact that there's many types of motor, and we're going to focus on just a few of them. We're going to focus on DC motors, the battery-powered type, the brushed ones in particular, and we're going to touch on servos and steppers as well. Brushless DC motors are becoming more and more common and more popular, and I suspect over the next few years we'll be seeing more of them in our projects. But for the moment, we're just going to say that they're out there and we're going to focus on the brushed motors, the servos, and the steppers, three very common things that you would control using an Arduino. There's also your entire set of AC motors that would plug into the wall instead of a battery or plug into the electrical mains. And there's induction motors, synchronous motors, and a whole range of different motors for different applications in the AC world as well. So looking at our brushed DC motors, there's a few standard properties that make them actually really simple to control. The motor direction is controlled by the polarity of the voltage. So if you swap your wires around so that positive becomes negative, the motor's just fine with that. It just runs in reverse for a while. Your motor speed is controlled by the average voltage. So if you're hooked up to a battery, your average voltage is the battery voltage. But you can also use something called pulse width modulation, where you turn your power supply on and off to the motor very rapidly. And if you've used an Arduino before, you'll know that as the analog out function, and you've probably used it to do something like dim an LED. The current draw from the motors is quite a bit higher than most other devices that we use when we're working with Arduinos, because the motors need to put out torque and they generate their torque through the interaction of magnetic fields within the motor. The stator coil and the rotor coil, or the permanent magnet in the case of a brushed DC permanent magnet motor, requires a lot of current to generate that magnetic field. And so we'll see these motors draw a lot of current to get torque. Smaller motors will often tend to be gear motors, and so they'll be able to spin at a higher RPM, but then use gear reduction to get torque, turning some of that additional RPM into torque while maintaining the same power output. Brushed motors are pretty cool because they're common. You can find them just about everywhere. They're cheap, easy to use. You just need two wires. The downside is they're not very efficient, and if you try to drive them too hard for too long, they'll tend to heat up. I know I just said that motors take two wires, and this is pretty standard. There's your two terminals on a little, $1 or $2 DC motor. If you've ever had a chance to have a dead motor like this and take it apart, just be amazed that somebody can actually make that entire thing for $1 or $2. There is such intricacy and fine detail that goes into manufacturing something like that, and they are just spit out on mass assembly lines in huge quantities. This motor over here, as the blue box indicates, has far more than two wires coming out of it. In fact, it should have six. And two of those actually go directly to the motor. The other four are for this device on the end called an encoder. There's magnetic signals on here, North Pole, South Pole, North Pole, South Pole, all the way around. And as this little wheel spins around, it flies past this Hall effect sensor right here, creating pulses. And those pulses come back down those four lines and let the Arduino know if you're running the right code on your Arduino. They let your Arduino know how fast the motor's spinning, what directions it's spinning, and how far it's spun. Servo motors are another type of motor. They tend to be based on a DC electric motor. So inside this servo right here, this one's kind of neat because it's transparent. You can see some of the gears. That's our gear reduction in the gear motor. And right in the back in here, inside the blue stuff, there would be a small DC motor in there. What you don't see in right about here in this part of the motor is that there is a potentiometer. very similar to the potentiometer that you use with your Arduino. And as you know, when you spin that potentiometer, you get a variable voltage signal coming back from it. Well, the potentiometer in here actually feeds into a little control board at the base of the servo. So there'd be one tucked away right in here, and it would read the position that the servo is in. And then it would figure out what position you're telling it to go to. And then that little control board right in there would figure out, do I need to spin the motor forwards? Do I need to spin it backwards? And how hard do I need to spin it to get it into the position that the human has told me I need to go into? So in order to talk to these motors, you have three wires coming out to them. You'll have your power and your ground typically, and then you'll have what's called a servo PWM signal. It's a little different from the pulse width modulated signal that we use going to our brush DC motors or our LEDs. It's not just a straight analog write command, because rather than it being a signal of how much power, it's a signal of what position the motor should go to. And so if you've got about a 1 millisecond pulse, your motor will want to spin fully to the left and stop. And if you give it a 2 millisecond pulse, it'll move fully to the right and stop. And if you're somewhere in the middle, about 1.5 milliseconds, it will move right to the middle and come to a stop. Now, those are rough figures. Different servo motors will have slightly different figures, and you can adjust them as you set up your control for that motor. So one of the great things about these is they will move into the position that you tell them to go to, and they will stay put right there, and they will fight somebody if they try to change that. So these can handle a load and stay in position. The cost of that benefit is that they do not have continuous rotation. They won't just keep spinning like a regular motor, because as you'll know if you've worked with a potentiometer, it's limited in how far it can spin, because you start at high resistance and go to low resistance, and then you have to spin back and forth. So you've only got about 270 degrees of rotation on these. So they're good for positioning things, but maybe not so good for moving things long distances. You can turn them into a continuous rotation motor. You can open them up. You can remove some of that sensing gear. And then what it ends up becoming is essentially a nice little DC brushed gear motor that has good gear reduction and its own speed controller built right into the board, because this board down in here not only serves as positional control, but when you hack it apart, you can turn it into your speed controller. Stepper motors are a little bit of a different game. They have 4 wires coming out of them, so you can see we're building up in our complexity a little bit right here. We've gone from the brush DC motor with 2 wires, the servo motor with 3 wires, and now we've got a stepper motor with 4 wires coming out of it. Some stepper motors will actually have 6 wires coming out of them, as you can see on this NEMA 17, NEMA 17 is the name for this size of stepper motor right here, and you can see that there's 6 contact points in here, but you don't need to use all 6 of those contact points. It'll run just fine with only 4 wires coming into it. And stepper motors are kind of neat, because if you grab them and twist the shaft, you can feel the individual steps as it goes tick, tick, ticking around. And typically a stepper motor will have somewhere around 200 steps all the way around. And you can amplify that by doing something called micro stepping, where you stop partway in between each step. And what that allows you to do is that allows you to spin that output shaft to the exact position that you want and hold it right there. So really good for CNC machines, 3D printers, and things like that. You can use those to drive belts. The catch is that the stepper motors don't actually have any feedback. You tell them to move a certain amount, and if they're stalled or overloaded, you don't necessarily know whether or not they've completed that command for you. And when you turn on your system for the first time, you don't know what position they were left in. So typically, if you're using a stepper motor, you have to run it until it hits a limit switch of some kind. So it's at a known position, and then you can count and keep track of the number of steps that you've told it to move, and hope that you've got a torquey enough stepper motor that when you tell it to move, it actually moves the distance that it's supposed to move. For our stepper motors, you'll typically use a custom driver chip. You can drive them directly from a microcontroller using standard motor drivers or amplification or even transistors to build your own stepper motor controller. But there are some more advanced chips that allow you to do things like current control so that you don't overheat your motors and waste power when they are stopped. Finally, we've got motor driver chips, and these really are the thing that allow your Arduino to control some amazing things. And they simplify the control down to the point where turning a motor on and off is no more complex than turning an LED on and off. Hence my favorite saying that if you can blink an LED, you can rule the world. Some assembly required, batteries not included, your mileage may vary. So motor drivers, think about your microcontroller. I say it's a WIMP. It's a WIMP relative to power electronics devices. Compared to a microcomputer, microcontrollers are very, very powerful at what they can do with their pins. For instance, an Arduino pin can put out 40 milliamps of current, which doesn't sound like all that much until you compare it to something like a Raspberry Pi that can put out 3 or 5 milliamps of current before that pin actually blows up. So microcontrollers are kind of wimps relative to motors, but as far as brains go, they're pretty powerful output pins. But if your Arduino is putting out 40 milliamps on a pin and your small motor requires 2,000 milliamps to get started up, then you're about a factor of 50 away from where you need to be, and that's where you need something to amplify your power. And certainly, if you're running a larger motor like the CIM motor that's very popular in the first robotics competition, you might need a couple hundred amps to get that motor started if it's under heavy load. And that's not going to be handled by anything that you see on this screen right here. You're going to need bigger, more powerful, heavier motor controllers than what we've got here. The other thing that's going to be different between your motor and your microcontroller is that your motor is going to run better at a higher voltage. Microcontrollers actually tend to run better at lower voltages. They give off less heat, which means you can run your processes more rapidly. And that's why, although the standard Arduino Uno runs at 5 volts, you'll see more and more newer and more advanced devices running at 3.3 volts. And although there are motors out there that will work at 3.3 volts and 5 volts, they really start to come into their own once you start getting up above 6 volts, 12 volts. And if you're looking for more powerful applications, 24 volts. And if you're getting into vehicle drive systems, well, talk to Elon Musk and he'll tell you about the current and power that some of his vehicles draw. Anyways, the other thing that's happening is that your brushed electric motors in particular make a lot of electrical noise. And that's got to do with the fact that those brushes are sparking when they turn on and off. You may have seen the brushes spark on a motor when it spins, and sparks are a big sign of electrical noise. And that means that you have voltage spikes and also negative voltage spikes that can be very damaging to sensitive electronics. So we're going to talk a little bit about how we can put protective diodes in place to protect some of our electronics. So motor controllers are really important when you go to use a microcontroller to control motors, and you can buy them off the shelf like this Seed Studio dual HBridge chip. So I can run 2 motors off of that, and each one can draw up to 15 amps. I can pick up an L293D, which is a very, very popular, relatively low-cost chip that can run a couple of motors fairly easily. If you need a bit more current, the L293D has a larger sibling called the L298. And there's also some clones of that. This one, actually, if you look closely at the number on it, is an SN754110, I believe. It's an L293D clone. We've also got, for our stepper motors, we've got modules like this. There's a number of different stepper module choices that you've got depending on the size and power needs of your stepper motor. And this little surface mount chip right here is actually the brains of the entire operation. And what that allows you to do is it allows you to use just 2 pins from your Arduino, one for the direction and one for each step that you want it to move. And as you send your pulses in here saying which direction and how many steps you want it to go, this takes care of creating the signals that turn the coils in the stepper motor on and off to get it turning for you. Finally, if you don't have access to any of these pre-made devices, you can just grab a couple of transistors off the shelf, and for a small motor, you can use them to get a small DC motor up and running. One transistor will get you on-off control because that transistor will amplify the power coming out of your Arduino. And for more complex circuits or something where you've got a little bit more power needing to be handled, you can switch over to using a MOSFET, a metal oxide semi metal oxide semiconductor. um, the acronym slips my brain somehow at the second. I know that one. Anyways, it's packaged in a TO220 package right here. You can get them in the TO92 package as well, but the TO220 is a little larger package, capable of handling more current and very importantly, dissipating more heat. Because often when you're dealing with power electronics, dissipating your heat is your biggest problem. Okay, so let's take a look at how we can control a small motor using one transistor. Now, if you've just got one transistor, that's going to allow for, let me bring this up and actually animate it. One transistor is going to allow for speed control, but not directional control. And that's what I'm looking for right here. Okay, so I quite like the website falstad.com because Falstad lets us come in here and just going to take all of this and drag it to the center of the screen. There we go, so we can see what's going on. Falstad lets us simulate circuits, and going to set that up and running. And right now, there's no electricity running through this circuit. Well, let's take a look right here. We've got a battery, power comes in here, and Falstad didn't have a motor, so I've used a light bulb to simulate that motor. And you can see right now there's no current flowing through it, and the motor is off. But when I close that switch, the motor turns on, and I've got electricity flowing through it in one direction. And when that switch is 100% closed, the motor will be turning at full speed because it's getting the full amount of voltage from the battery. But if I open it, then it stops. And if I close it again, then it starts up again. And if I open and close it really, really quickly, you can see that the motor is still getting current going through it, but just not as much current. My average voltage, my average current also through the motor has gone down because I am no longer providing it with power 100% of the time. Now, that's using a physical switch right here. And using a physical switch is fine. Yeah, it's an on-off switch for the motor, but it doesn't provide you the type of logical control that you'd like from your semiconductor devices, from your microcontrollers. So what you can do is you can bring a transistor and put it in line right here. And here I've got an NPN transistor, just a standard NPN. And as you'll recall, with an NPN transistor, electricity flows from the collector through the transistor and out the emitter when there is a small voltage or tiny little bit of current coming in on the base. So basically, I tend to think of the NPN transistor as essentially being a push button. If I put a little bit of electricity pushing on the base, then I turn it on and electricity flows from the collector and out the emitter. And if I don't push on the base, then this is like a switch that's turned off and nothing flows from the collector to the emitter. So right now, I've got this switch right here tied into the ground line, so my base is not being pushed and my transistor is off. This is the same as using the digital write pin comma low command, and if you were hooked up to an Arduino right here, right now you would be sending a low signal right here, and your Arduino would be telling this transistor, hey, turn off, don't let any current flow through you. So what we can do is we can switch that over to a high command, and now you can see we've got electricity flowing right through here, and the signal that we would have coming from our Arduino would be right here, would be hugely tiny. and not a big deal at all. Totally within the Arduino's ability to handle sending a signal like that, because all your Arduino would be doing is sending the signal to the base, saying, "Hey, transistor, time for you to turn on right now." And again, if you want speed control, well, now that's pretty easy to do because your Arduino can handle switching that on and off. And as you switch that on and off, depending on how much time you spend in the on position, your average voltage across the motor goes up, your average current through the motor goes up, and the average speed of your motor goes up. So you can get speed control with a single transistor, but you won't be able to get directional control. If you want directional control, you're going to have to get a few more uh, transistors involved. And here we've got this set up, and let me select all of this and drag it back. I don't want to switch, thank you. There is a center command in here somewhere, but let me just hit escape and highlight this all and see if I can drag it all over or off the screen right there. Doesn't do very good to leave half of your HBridge behind. Come over there and join it all together. All right, so let's take a look right here at just a switch-based HBridge. Now keep in mind that the direction that the electric motor turns is based on the direction that the electricity flows through it. And right now we've got our electricity, positive current flowing out this way, coming down right through here, through the motor, turning the motor in this direction counterclockwise, and then coming out through down here. Let's just stop that for a moment right here. And now we'll make this side positive and this side go to ground. And now you'll see that the electricity is flowing this way, coming down right through here, passing this way, and that will be turning the motor in the clockwise direction. We've reversed the direction of the motor by changing the position of the switches. Now you do have to be a little bit careful about which switches you turn on and which switches you turn off. Obviously, if all your switches are off, then no problem. There's no current flowing anywhere. And if you turn the top two on, well, you've still got no current flowing anywhere because there's the same voltage on each side of the motor. Same thing happens if you turn the bottom two on. Nothing's going to happen right there. In fact, what you'll actually get is a motor braking effect, where if the motor's still spinning, the electricity that the motor generates will form a little loop right in here and come back and push on itself and cause its own self to slow down. So if you've seen cordless drills or cordless power tools that have braking, that's how they're doing it. They're messing around with the H-bridge and giving it some interesting directions to go. One thing you do have to watch out for with manual H-bridges like this is that if you turn this switch on and this switch on, you're going to run into a problem and it'll all shut down because you'll have a short circuit right through there, and your circuit will just say, "I'm not doing anything more for you." So that's how we can control the motor's direction. And again, if we turn the switch on and off fast enough, we can control the speed fairly smoothly, the average speed that the motor is putting out. And we can get that average so smooth that nobody notices that we're actually flicking a switch on and off really fast. So one direction, off, other direction is how we can control those motors. Now we can do the same thing with transistors. And with our transistors right here, you can see that I've got two different types of transistor in here. You can do it all with NPN transistors, but it's kind of fun to use a PNP on the top side and an NPN on the bottom side. Now, keep in mind that an NPN transistor turns on when you'll provide a little bit of current to the base. A PNP transistor turns off when you provide a little bit of current to the base. So in this case, when I set this switch to go high right here, the high voltage comes down right here, passes through the two resistors. The high voltage turns off the PNP transistor, but turns on the NPN transistor. And if I swing the switch over right here, Now this goes low, and this will turn on the PNP, okay, because we've got electricity that can scoot out that way, which enables that one to flow. Just sort of watch the arrow, and if it scoots out that way, then it's good to go through this way in much, much greater quantities. And down here, well, there's nothing coming through this way, so nothing can get through right there. Let's see what happens if we turn that switch. And now, in this configuration, we've got electricity coming from right here, passing through right here, turning it clockwise, coming out here and getting back to ground. Very important that it's able to get back to ground and get back to the original power source. And using the NPN and PNP, PNP and NPN transistors in here also makes it more difficult to short out either side because you're either on or you're off on that side. Here we go. We've thrown this one up. This one now disables this transistor, enables this transistor. This one's enabled. Electricity flows down through here, rotates it counterclockwise, and then comes out here and back to ground. Now, there are a few things that we need to watch out for when we're hooking this up. And one of those is that voltage spikes can sometimes happen. When the motor is spinning, that big flywheel inside, well, it's not a flywheel per se, but that rotor acts like a flywheel and it stores lots of energy. So when I turn the motor off, that stored energy inside the motor still has to get out. And it's not just the mechanical energy of the spinning motor, but it's the electrical energy of that magnetic field that's been built up around the coils. And that's something called induction. And that inductive magnetic field around the motors, you can almost picture it as, I like to picture it as like the electricity being like a freight train. Okay, and when you get a freight train moving, it takes a little while to stop it. And so picture this as a big freight train coming through here, and somebody suddenly trying to slam on the brakes. Well, if you put a brick wall in front of a freight train, you're going to have a bad day. And you're going to have some energy spikes when that freight train hits that brick wall. And that's what we're doing right here when we're suddenly turning this off. So what we'll sometimes do to help protect against that is we will add some diodes, and we'll add these things called protection diodes that will come in right here. Now, if we add that right there, then the electricity is just going to go straight down to the ground. What we do is we put it up that way. And you'll say, well, why would you do that? Because electricity will never flow through this way because the voltage up here is always higher than the voltage down there. Well, I don't want that. I want it going the other way. And down here, you'll say this is ground. The only way electricity could flow from here is if the voltage at this point dropped below ground. And same thing right here. We put one on that side and one on this side. And what that does is that protects those transistors right there. Because sometimes when you slam that motor into a stop, because of that inductive freight train effect of all of the stored energy in the spinning motor and in the magnetic field about the coils, that will come to a sudden stop, causing a sudden voltage spike in this side that can either drive it up higher than your battery voltage, in which case, instead of it going into your transistors, that voltage spike comes back here and gets absorbed by your batteries, or it can suck that voltage down, in which case this line would drop below 0 volts, causing a big problem right here. You can think of it as kind of being like a vacuum effect, the vortex left behind. You know, you felt that when a semi-trailer truck goes past you or something like that. There's that big sucking vortex where the air pressure behind the truck is actually lower than ambient. It's just temporary and it's localized, but that's what can happen right here. And this allows electricity to flow in, fill up that big sucking voltage vortex, and prevent damage to your chips. So if you hear someone talk about protection diodes in a circuit, these protection diodes are actually quite important to making your circuit work reliably. We'll turn that back on. We'll get some electricity flowing through right there. You'll sometimes also see a switch called an enable switch. And the enable switch is basically a master on-off switch for your H-bridge. Before I started adding the diodes, I should have pointed out the reason it's called an H-bridge is you can see one leg of the H right there, the crossbar of the H right there, and another leg of the H coming down right in there. So it's called an H-bridge because it kind of looks like an H when you draw the schematic out. And there's an enable switch for a lot of this stuff that it's just another transistor. I've modeled it with a switch right up here. And you can use that as your speed control if you want. You can use two microcontroller outputs, one each for the controlling the switches on each side to control direction, and then a third one to turn it on and off. If you really want and you're trying to save microcontroller pins, you can just hook that into your plus 5-volt supply and leave it always turned on and do your speed control by flicking one of these two or both of those two on and off as you see fit. Okay, so that's a couple of models of how the H-bridge works on Falstad. Let's go to TinkerCAD and take a look at how we would model those up in TinkerCAD. Bring that in over here. So here we've got a few things that I've put together already in TinkerCAD. So just a reminder that you go to TinkerCAD and over on this side of the screen you'll see the option for circuits, and it's always a good idea to log in with your account so that you're right up there, and that way you can save it to your account, and you can also share your files with people so that if you're running into a problem, people can see what's going on. I'm just gonna delete that. I've been playing around with this a little bit right here. So some of the components that we've got in here, I've got the Arduino and the breadboard, and if you're looking for that, it is, come to your starters and just go to Arduino, and right there you'll find an Arduino with a breadboard hooked up, and you can bring that in. And when you bring that in, you'll see that it's got an extra red line right in on the breadboard right there. I've already got one of these in here, so I'm going to just get rid of that. But that line right there is one that you're going to get rid of. There we go. Okay, so we can bring that in right here. And now we've got our ground line hooked up to our Arduino's ground. We've got our 5-volt line hooked up right here. But this side, and only this side, we remove this red line right here so that this side is the only one hooked up to the Arduino's 5-volt, because we want to bring in a battery. So we can come over here and go to all of our components, and you can scroll down, and somewhere in here you will find a battery. Look at all those cool things to add: breadboards, microcontrollers. Did I go past the batteries already? Anyways, you will find a battery right in there. I promise you, you'll find a battery. Pixel. There we go. And I just used the 1.5-volt battery here. And then when you bring that 1.5-volt battery in, you can tell it what type of batteries you want and how many batteries you want. So with 4 1.5-volt AA batteries in series, I end up getting 6 volts coming out of that battery pack. And so what I'm going to do is I'm going to hook up the negative line, the ground line right here to along here, and I'm going to hook up my 6-volt line right down here. So I've got a different voltage in this header strip than I do in this header strip. But what's really important anytime you do this is that you all share a common ground across all of your circuits. So this battery and the microcontroller are both at the same 0-volt level, so that when we turn things off or set them low to 0 volts, we know what that means. Okay, so we've got a nice little 6-volt battery in here. We have a common ground between the motor battery, our Arduino's power supply, and the breadboard. And we've got separate power supplies. One at 6 volts that's going to be capable of delivering quite high current, sometimes up to several amps if we need it. And down here, we've got your Arduino's power supply coming in right here that's going to give us 5 volts right along here, but probably not more than about 500 milliamps, because if you're running this Arduino off of your USB port, most computer USB ports are limited to supplying about about 500 milliamps. USB chargers can deliver more than 500 milliamps, in some cases up to 2 amps, or even 3 in some extreme cases for tablets and things like that. But we don't want to run that much power through the Arduino when we can run it directly from the battery pack. Okay, now in here, you're going to find that we also have a whole swack of motors, and the simulator is really cool that way in that they've thought about all these different devices that we can add in. And there we go. I was going to say, I don't know why I'm unable to find anything today. Here we've got a DC motor, with an encoder. So if you think back to that second or third slide that I showed you, there's just your plain old motor. There's your DC motor with an encoder. They've got a couple of different sizes of servo in there. So they've got some really neat stuff for you to take a look at. And they even have a little hobby gear motor like we used on that BoomBot back on the first slide. And we can bring that in here and we can turn that motor on and off. And just so it fits a little bit nicer and we can still see what's going on, I'm just going to take that and I am going to use the rotate button to rotate that motor into position right here. And let's just hook it up and see what it does right now. So here's my negative line from the motor, and I'll hook it up to the negative from my battery. I'll take the positive and I'll hook it up to the positive, and I should set these wires to the right color. Not that the electrons care, but if you get in the habit of doing neat and tidy breadboarding now, you'll probably keep up when you do neat and tidy breadboarding for real. And if we start the simulation, we don't even need any code right here. You can see our motor kicks in and it's spinning at 187 RPM. And maybe I should have just used the regular DC motor because it's hard to see the direction that this one's spinning. Let's just stop our simulation right here. And let's reverse the direction that our motor's hooked up on here. So I'm just going to delete this wire that had been hooked up to ground. And now I'm going to hook that one up to the positive. And I'm going to hook this one up to the negative and start that simulation. And now minus 187 RPM. So it does tell you which direction it's moving. So even though we don't necessarily see that, you can see that the motor's spinning back and forth. Now, as I said, a motor's speed is controlled by the voltage going to it. And right here, we have a 6-volt battery because we've got 1.5 volts plus 1.5 plus 1.5, 4 times 1.5 is 6. And when they're hooked up in series, you add the voltages together. When they're hooked up in parallel, you add their current capacities together, but this only lets us hook it up in series. Let's see what happens if we switch to a 2 battery pack. That drops down to 97 RPM. Let's go back up to 4 batteries, 187 RPM. So we're going quite a bit faster. Okay, now that is just hooking the motor directly up to a battery pack, and that's not particularly impressive. So let's take a look at how we could control that using a transistor. And just as our Fallstat example showed us, we're going to come in here and we're going to pick up an NPN transistor. They're in here somewhere. I've got all the devices turned on, so it takes a while for me to, there we go. There's an NPN transistor right here, and I am just going to drag this in like so and put it in there. Now, do take a look that when you take a look at the transistor model in here, that it is a collector base emitter transistor. Okay, many transistors that you use will be an emitter base collector transistor. Some out there go collector base emitter because apparently standardization was just too good for some people. Anyways, what we're going to do is we are going to take our positive electricity from the battery and we are going to run it right up to the motor. So now electricity is coming from the battery right up to the motor right here. And if we just connected that line back to ground, it would run. We just saw that. What we're going to do is we're going to route that electricity back through. I want to get in right behind it right there. Come on, let me get in behind. Okay, let me move this transistor down so that I can get in right behind it. So now the electricity is going to come out of here. It's going to come to the collector, and then it is going to go back to ground through the emitter. So I've got that hooked up as black. So let me just put that back into place. So I've got a little bit down on here. So now what's happening, we want the electricity to come down here, up through here, down through right here. The transistor is going to act like a switch, and when the switch is on, electricity can come back that way and go back to ground. And what we're going to do is we're going to throw a resistor in line right here. Okay, so the resistor comes to the base, and we can, I have to remember to turn off my email when I record these things. 1K ohm resistor will be just fine because we don't need any real current going that way. We just need enough signal to turn the base on and allow the transistor to start transmitting. And what we're going to do for right now is we're just going to take this and connect it up to the red wire right there. And we're going to start our simulation. And there we go. Now you'll notice that before we were running at 187 RPM, we have lost just a tiny little bit of voltage through the transistor. There's about a 0.7 volt drop when things go through the transistor, so we're not running quite as fast as we were before. So anyways, that's that energy that's being lost as the voltage goes through the transistor is going to cause that transistor to heat up, which is why we can't use a little transistor like this for a really big motor. The transistor would overheat and explode fairly quickly. Okay, so we know that works. Let's just take this wire right here and see if we can move this end. Let me select that wire. Let me delete that wire if it doesn't want to cooperate, and just put a new wire going directly to ground. And you can see that when I make this signal go low, the motor is stopped over here. So now what we can do is, rather than just plugging wires in to make that go on and off, we can take a wire and we can run it from our resistor straight over to pin 3 on our Arduino. And I'll just, let's make it orange just because we can. So now what's going to happen is our Arduino is going to be able to set this to high or to low. When it's set to high, that voltage is going to come through right here. It's going to push on the base. It's going to turn on the transistor, and that's going to allow electricity to flow from the battery down through here, up to the motor, down to the transistor. Since we've got the transistor turned on, the electricity will flow through here and back to ground, and the motor will spin when this pin is high. And if we put that pin low, then the transistor is going to turn off and we're not going to have anything flow. So let's come in here and take a look at our code. And in the code right here, and if you need to get to here, if you're stuck in the blocks routine, remember, just do a little drop down right here and you can come to text. You can write this code using the blocks if you want. It's not a big deal one way or the other. But come in here, and here's our setup routine. And we're using pin 3, so we remember to set pin 3 to be an output. We're going to do a digital write on pin 3. We're going to set it high. We're going to delay, let's delay 100 milliseconds. Then we'll digital write 3 to low, delay 100 milliseconds. Okay, so basically this is your blink routine. Like I say, if you can control an LED, you can control a motor, frighteningly enough. Let's start that simulation. And now you can see the speed of it is fluctuating.
And so sometimes it's showing 0, sometimes it's showing 187, and that's bouncing back and forth right in there. Just going to close the code window right here. And if we come down and take a look at our oscilloscope, the oscilloscope's kind of nice because that lets us have a view of what's going on at the motor. And we'll take our negative line and we'll hook it into the common ground. Okay, and let's take a look at what's happening right over here on the positive line. Start that simulation up right now. And what you can see right here is that there is a pulsing happening right on here that's being controlled by our Arduino. Okay, let's turn that off. We don't need that in there anymore. Let's see if we can change the speed of that motor. So if we come into our code, okay, well, we were turning it on and off 10 times, on 5 times a second and off 5 times a second because there were 200 millisecond delays. If we go faster, okay, instead of it going vroom, 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 and turning on and off, now we're going to start our simulation right here. And you can see that instead of having the RPM flash back and forth, it's settled in at a fairly steady 90 RPM, which is about half of the 187 that we were getting when the motor was on full time. So that's because right now the motor is on only half the time, but it's turning on and off in such tiny little bursts that that we don't even notice it. Now, stop the simulation right there because there is a little thing that the simulation's letting us get away with that you may or may not be able to get away with in real life. And that is we do not have a protection diode right in here. So because we're turning that motor on and off very fast, what we should be adding in here is a protection diode. Okay, and that protection diode should be such that if this pin gets drawn down below ground, actually I don't want to put that right there, I want to rotate it a little bit. Okay, so if this pin gets drawn below ground, so that this voltage gets less than ground, we're going to have a diode that lets current flow that way. And if the voltage gets above our supply line right in here, okay, then that's going to let it go down. Let's bring in another diode right over here and rotate it so that our cathode's pointing up that way. And now I'll hook that into the ground right there. And now on the collector right here, if that pin ever gets pulled lower than ground, electricity can flow through the diode. And if it ever gets popped higher than the supply voltage, electricity can come out there and go back around that way. And that will make your transistor work a lot happier. Our simulation lets us get away without having to do that, but in the real world, you might not get quite so lucky. Sometimes people will also put capacitors across the two leads. Make sure that if you do that, well, if you're going only in one direction, you could use a polarized capacitor. But if you're using an H-bridge to go in two directions, you wouldn't necessarily want to use a polarized capacitor for that. Okay, so that's a neat little simulation right there, and you can write code to make your motor run. Let's stop that for a second and take a look at our code. Now here we're manually turning that pin on and off, but of course you can see the little tilde sign, the squiggly line next to the 3 on the Arduino, indicating that that pin supports pulse width modulation. And in the Arduino world, the pulse width modulation is controlled by the analog right command. And we're going to set pin 3. And analog right, if you put a 0 after the comma, is going to be all the way off 100% of the time. If you put 255, the highest value that you can store in a byte in there, it's going to be on all the time. And if you put something like 128 in there, which is halfway between 0 and 255, it's going to be on half the time. In other words, it will have a duty cycle of 50%. So we should be able to come in here and say start the simulation. And there we go. We're having the same effect that we had by turning it on and off very rapidly, 50% of the time, 50% off. Now we're just using the analog write command to do it. Let's stop the simulation right here. You can try a few different things with that. So for instance, the for loop, for integer speed equals 0, speed less than 255. So we're going to do a loop from 0 to 255. Okay, and we're going to increment speed by 1 every time we go around this loop. And then we're going to put a little delay in here, delay 10, so it'll take a couple of seconds for it to get up to speed. And our ellipses, our squiggly bracket right in here. So this will come along, it will start with speed equals 0. And instead of analog writing 128 right in here, we're going to write our speed out right here. So we start with a variable. The variable is going to increase, and we're going to loop around this 255 times and slowly watch that speed increase. And there you go, over the course of about 2 seconds, you can see that speed comes up to about 180. If you want it to go a bit slower, try setting this to, oh, we got to stop the simulation. Try setting that up to 50. And now you can see it slowly ramping up on your speed. So that's one way that you can hook up a standard DC motor, and you can control its speed. It might be possible that you would want to control the speed using a potentiometer. So you could put a potentiometer on there, and as you turn the potentiometer, you could control the speed of your motor. You could also take it and you could put another input device. So we took a look at rangefinders last day, and if you were making a little robot, you could take 2 of these motors and use them to drive around. You could put your rangefinder on there, and you could have it when the rangefinder detects you getting close to an object, you could make that motor turn. So there's a standard DC motor all hooked up and running with a little bit of Arduino code. Do you think you could build one with an HBridge? Shouldn't be that hard. I'm going to pause right here. I'm going to build an HBridge. Why don't you hit the pause button, try building an HBridge as well, and let's see if yours looks anything like mine.
And just like that, it's all done. An HBridge, what do you know? Now, to be perfectly honest, I didn't get it on the first try. But I went back and I looked at my schematic from when we were talking about the HBridge, and I said, okay, I've got the 2 collectors joined together here for my NPN and my PNP, and I've done that on both sides, forming that H. One side goes to high voltage, one side goes to low voltage, and the bases come out and through a resistor, they collect. I wanted to move the whole screen there, just a minute. And through the resistors, they connect down to pins 5 and 6 on the Arduino. Over in my code, I make sure pins 5 and 6 are both set to outputs, and then I'll digital write 5 high, digital write 6 low, and that'll start it turning in one direction. I'll put a delay in for 500 milliseconds. I'll digital write 5 low and 6 high, reversing these two pins right here. That should turn it in the other direction. Do that for 500 milliseconds. Set them both low. That should turn it off. And wait for 500 milliseconds. And then I'll digital write 5 low, which puts this one down low, and then I'll run analog write on pin 6 at 128, which turns this on and off half the time, so it runs at half speed. And then to flop the direction, I just need to change the other pin. Now, that's a little bit of a hack because it only works when you're at 50% duty cycle, because 50% forward speed is 50% reverse speed. If I had something other than 128 in there, then I would also see a change in speed. So how does it work? Well, let's take a look right here. And there we go. It reverses, stops, and we can see that little motor spinning, stopping, half speed, circling back and forth in there, and we have full HBridge control of it. Now, that's how you can build a little HBridge just using transistors. We're going to keep the code pretty much the same, and let's see how it goes a little bit easier if we use the L293D. Okay, so the code works the same, but now all of those functions are built into the L293D chip, and what's really cool is they're built into just one side of the L293D chip. So now you may have to go back in the presentation a little bit earlier when you were hooking this up to take a look at the schematic for the L293D and note that this pin right here indicates pin 1. And if you mouse over top of each of these pins, it tells you what each one of these does. Okay, it's not necessary to hook all 4 of your ground pins up to ground so long as one of them is hooked up. These are all electrically connected inside, and the main reason we've got 4 ground pins on here is actually for heat dissipation. The chip uses those pins to get some of the heat out of the chip. And so once again, here we go. We can start that simulation. And we've got the motor spinning forwards and backwards. So you could add another motor right in here, and you could have the 2 motors controlled, and that would be exactly the same as the BoomBot that we showed you in the second slide. Now, this is kind of ugly for wiring. I threw it together quickly. If I was going to submit this for marks or something like that to show what was going on, I'd probably tidy up some of the wiring. But you will notice that I do stick to a couple of core features even when I'm doing it fast. Anything that goes to a ground line is black, and anything that goes to a power line is red. Now we should probably use a slightly different red. Maybe we get away with an orange or something like this on this line because this power right here is different from this power right here. So there we go. That's a couple of quick ways to hook up motors in TinkerCAD and program them with your Arduino. And this code that we've generated right here and this breadboard setup will work in the real world exactly the same way. So that's a pretty cool feature about the TinkerCAD simulator. So those are 2 examples of DC brushed motors, and you've certainly got the opportunity to build another brushed motor in right here and control that brushed motor maybe by using an ultrasonic rangefinder to have the motors spin forwards until you come to a stop. Have them spin forward until your range becomes too short and then have the motors turn off, or have one motor keep going forward and the other motors start going backwards so that you turn until you've got some range and then your robot could go forward.
You could also bring in a couple of other sensors, and you could emulate a line following robot using this. So some really neat stuff that you can do in the TinkerCAD simulator.